Greetings, everyone. Let's talk about gravity and how it determines the behavior of planets in our solar system, all the way up to stars and galaxies. So we've all heard the legend of how Newton discovered the law of gravity, right? There's an apple that fell down. But this apple started off with a v equals 0. When it hit the Earth, it certainly didn't have a zero velocity anymore. Its velocity is now, some negative number, maybe, I don't know, minus 9.8 meters per second or something. So after a second later, this will be its velocity. So if gravity reaches to the top of this tree, then Newton supposed, then gravity can reach all the way from the Earth all the way up to the moon. And it's this kind of imagination or supposition that makes these people like Newton and Galileo just incredible geniuses, to be able to take what they learned from an apple falling down and be able to apply it to the Earth and the moon. Basically, since this apple is falling down, it falls down how far in 1 second? So an apple falls down, we know there's v initial t plus 1/2 a t squared. So if its initial velocity is 0, then this distance that it falls in 1 second is just minus 9.8, now times 1, so minus 4.9 meters. So this is how far the apple falls down in 1 second. We can just write this as xa, and just for bookkeeping, we're going to keep this over here, is 4.9 meters, how far down it falls. How far does the moon fall down in 1 second? So basically, what is xm? So how far does it fall in 1 second? So there's two ways that Newton went about checking this and checking his universal law of gravity. One was that he looked at how the moon, we know that the moon goes around the Earth, okay? And the time that it takes the moon to orbit, right? This is, so it orbits every 29 days, so 29 times 24 times 60 times 60, this many seconds. And we know the radius of the moon's orbit, and this is about 60 Earth radii. And we know the radius of the Earth is about 6,400 kilometers. So from this, you can figure out how far the moon falls in 1 second. So basically, here again is the moon, here is the Earth. So the moon is going this way, right? And then we want to know how far does it fall. So this is the x of the moon. So basically, you can take this information and extract x of the moon is about 0.00136 meters. But there's another way that he could check this information. He could use his universal law of gravity, which is that the force of gravity is equal to this. So mass of the Earth, mass of the object, all over r squared. This r squared is the really important part here. Basically saying as you go farther away, there's this inverse square. So if you're twice as far away, then the force of gravity is going to be 1/4 as big. And then this value right here is the gravitational constant. And then this is the mass of the Earth, or whatever other object you're considering. And then this is the mass of the, satellite, or whatever else you're interested in. So if we know this, and we know that force is equal to mass times acceleration, then we can say that x of the moon over x of our apple, basically, should be equal to the acceleration on the moon times the acceleration of the apple, right? Because here we have just in 1 second, here A is proportional to X, right? So then we could find out what this XM is. So this XM is going to be equal to our apple is going to fall 4.9 meters in 1 second. And then now we just need this A of the moon. So A is equal to, mass, right? The object's mass, and then now this force is equal to all of this. So this acceleration is equal to G mass of the Earth all over the radius of between the Earth and the moon squared, all over GME all over radius of the Earth squared. So this simplifies a great bit, actually. All of this stuff goes away, and in fact, this radius of the moon, RM, is 60 Earth radii, pretty close. So then, when we simplify this, we're going to get this 4.9 and then 1 over 60 squared. And this is exactly equal to this value right here. So this is one way that Newton showed that his law of gravitation was working, in fact. So we're going to be looking at this law of gravity, this equation right here, and then also talking about some other useful ways of thinking about gravity and how these heavenly bodies move. But basically everything comes down to this. Even Kepler's laws all derive from this relationship right here. What is the escape velocity of Earth? So what do we mean by that is if you look at the Earth and you wanted to, blast a rocket off, right? And you wanted to have enough energy so that it's going to escape out of the Earth's orbit. We know if you just throw a ball up, it's going to eventually fall down, right? It's going to go like this. But if you throw harder, it's going to go like this. And then if you shoot rockets off, maybe it can escape the Earth's gravitational field. But what is this velocity that we'd need? So the easiest way to do this is to look at conservation of energy. So the initial kinetic energy plus the initial gravitational energy is going to be equal to the final kinetic energy plus the final gravitational potential energy. So now we need to know what this U of the gravity is, because gravity near the Earth's surface, we know, well, we've been told this gravitational potential energy is equal to this mgh. But this is an approximation for things that are near the Earth's surface. That's what this G tells us. But this is just an approximation. As you get farther away from the Earth's surface, this will not hold up. But basically, this potential energy is like a work, and a work is like a force, the integration of force times a distance, right? But here, this force is changing with how far away you go. So what is this force? This force is Newton's gravitational law, so mass of the Earth times mass of the object, right? All over r squared. And now we're integrating it with dr. And we start near the Earth's surface, and then we go very far away. If you want to escape the Earth's gravity, you need to get infinitely far away. So let's solve this out, this integral. So we're going to get a minus gm of the Earth, mass of the object, all over r. And then we need to evaluate this where we're starting and then where we end up. So the nice thing is when you plug in infinity down here, you're going to get 0. So this is really just minus gm of the Earth, mass of the object, all over r of the Earth. So we end up very far away, so this potential energy is going to be 0. So let's start with our initial part. So Ki is going to be 1/2 mvi squared. And then now we're going to add on our potential energy. So this is a minus m all over re, the radius of the Earth. And this is going to be equal to, if we just want to get out of the Earth's gravitational field, we want to get to that point with no kinetic energy left over. So that's 0. And then this final potential energy, if you plug in an infinity here, you get a 0. So that's plus 0. So this looks very strange, but so you start off with both kinetic energy and gravitational potential energy. You end up with nothing. But another way to think about this is that if you look at U, so this U is over R. So as you get closer, let's use a different color. So as you get closer to the Earth, this diverges. So basically you want to escape this whale. You want enough energy, right? If you sit right here, here's the radius of the Earth or something. So you're sitting right here. You want to add enough energy to get you out of this whale. And this is the kinetic energy that we add on to this. So let's go ahead and finish this. So then V, if you work this out, you're going to get square root of 2g mass of the Earth divided by R. So you'll notice that the mass of the object doesn't play a role in this. But the radius that you start off with does. And so does the mass of whatever planet that you're on. And if you work this out for the Earth, so just a couple numbers for the Earth. So the mass of the Earth is, well, it's about 6 times 10 to the 28th, or 5.98 times 10 to the 28th kilograms. And then R of the Earth is about 6 million meters. And then G, this universal gravitational constant, is 6.67 times 10 to the minus 11. And the units on this guy are one thing you have to kind of watch out for. But the way you can remember it is, here you have two masses and then an R squared. So what you want is newtons to end up here, and you're dividing by R. So it means you have to, this guy has to have R squared. And then now you need to go kilograms in the bottom here to cancel out both of these kilograms in the top. So 6.67 times 10 to the minus 11. When you plug all these in, you're going to get about 11,000 meters per second, or 11 kilometers per second. So this is about 30 times the speed of sound. All right, so before Newton, there were a bunch of other people who were interested in seeing how the moon and Jupiter and Saturn and all of their moons, how they behaved and being able to describe their motions. And Kepler built on Copernicus' theory, and he came up with these three laws. One is that planets move in ellipses, and the sun is at one focus. So if you have an ellipse, you know that if you take a string, right, and you make a loop, then you can draw an ellipse by like sticking your pen here and then just keeping the rope tight. These two, whatever pins right here and right here, these are the two foci of the ellipse. So that's not too important. So the sun-planet line sweeps out equal areas and equal times. That's pretty confusing too. But if you look at how the moon, let's just say the Earth. If the Earth was at this place, and let's say maybe a month later, it's going to go over here, so it fills up this amount of area. But if it were farther away, like over here on this side, then about the same amount of time is going to fill up the same amount of area. And if it's going to fill these two areas, this purple and green, both have the same area. So what it means is that this velocity, this blue velocity, is bigger than this green velocity. So if you're closer, if you're in the part of the orbit where you're closer to the sun or whatever, then you're going to be moving faster. And if you're farther away, if you're at this point, you're going to be moving slower. But a more useful, at least for us, of these Kepler's laws is this, where the period squared is proportional to this radii to the third, and then there's this bunch of constants here. So all of these guys are just constants that we have to keep around. So this is the mass of the sun in our case. So the mass of the object that we might care about, maybe the Earth or maybe some asteroid, it doesn't matter. Basically, all that matters is the mass of the sun here. And then the period is related to how far away it is, given this relationship. So let's work two examples with this. So we have some satellite that's circling around Mars. So here's our Mars, and now we have some satellite. The satellite is 100 kilometers above the planet's surface, but that's not really what we want to know. We want to know from the center of Mars, basically. So what we need to do is add this radius of Mars, so 3.4 times 10 to the 6 meters, plus 100 kilometers, that's 10 to the 5th meters. So then you're going to get 3.4 times 10 to the 6 meters. And then we have the mass of Mars, we have the gravitational constant. We want to know this period. So this period is t squared. And then all these constants, right, 4 pi over gm. And then now a to the third. This a is going to be this guy. We're going to plug that in. So now we actually have all the information that we want to know. We just need to solve for this t. So then t is going to be the square root of 4 pi all over g. I don't want to write that guy out. Mass of Mars, so this is 6.4 times 10 to the 23rd kilograms. And then now A is our 3.5 that we just figured out. And then we have to cube that. And we're going to get 6,287 seconds, or about 1.75 hours. So this is traveling at an incredible rate in order to orbit at this height. All right, for our last problem, we're going to be using Kepler's law again, but this time I'm going to show you a neat trick. So we have this asteroid, and it's in some nice circular orbit around the sun. So here's our asteroid, and then here is the Earth. They're both traveling like this. And why do I put the asteroid out farther? Because its orbital period is bigger. So now I want to know what is its distance from the sun. I certainly could use this and then look up what is the mass of our sun. That's like 2 times 10 to the 30 kilograms. And then I could figure out whatever else I wanted to know. But there's an easier way. Basically, we know that the Earth's period is equal to, all of this stuff is just some number, some constant. And then now times the R, or this A of the Earth. And then now we can do the same thing for this asteroid. It's just some constant times R of the asteroid cubed. What we can do is divide this guy, this second equation, by this first one. So we're going to get TA over TE squared. This guy's squared over that guy's squared. And then I'm just lumping them together. And then now these C's are going to go away. But I'm going to get RA over RE to the third. So this guy's to the third, this guy's to the squared. What I know is that the orbital period of this guy is 8 years. So what is the orbital period of the Earth? That's 1 year. So then this quantity is 8 squared. And then what I want to know is RA, and then I'm dividing by RE. So 8 squared, and then now I'm going to take the cube root of that. So RA over RE is equal to 8 to the 2/3. So this is 64, and then now we take the cube root of that, and what we're going to get is 4. So what this means is that RA, whoa, that's not an R, RA is equal to 4 AU. So AU is the distance between the Earth and the Sun. That's one astronomical unit. It has this distance right here. So we could figure out exactly in meters how far this asteroid was orbiting the Sun. But working in AU is a lot easier. So this asteroid is 4 AU away from the Sun.